Hello everyone, and welcome back to Reverse Engineering Linux 32-bit applications. In this video, we're going to continue our discussion of stack buffer overflows, and in particular, we are going to talk about GOT, Global Offset Table overwrites, and dereferences. So first off, what's a GOT, a Global Offset Table? We talked about this in a previous video. This is a table that stores the location of library functions. Now we said that we had a PLT, which was used in order to call library functions in our application. And this is something that is also involved in that process. So the PLT had locations for places that you could call, things that you could call into your library functions, and actually it will update the GOT and then use that. So when it comes to attacking the GOT, there are two basic ways of attacking it. You can either overwrite the entries in the table, or you can do what we call a dereference attack. So what is a dereference attack? You store an offset in a register, and then you use a method that will call or redirect, if you will, to a certain address based on what's in that register. So, how do you know where these entries are? You can use objdump -R and then the name of your program, and that will show you where the GOT entries reside in your program. And we'll show you how to do that in a little bit here. So GOT overwrite, a little bit more about that. First, you have to find offsets for a called function and your desired function. So how do you do that? You use readelf-s on your library. We've done this before in order to calculate these offsets. Once you have the location of the function that was called in the library and the function you want to call, you can calculate the offset difference, the delta. And it's pretty easy to calculate. It's just the desired address, the thing you wanted to call, minus the called address, the address of the thing that the program actually calls. So once you have that delta, what you can do is you can overwrite the entry. So you overwrite GOT, the entry for the called function, with GOT for the called function plus this offset delta. So now once you've done this, every time someone calls the original function, it will actually call your new function. So this is one method of using the GOT in order to exploit some vulnerable software. What's another method? GOT dereference. So GOT dereference is another way that you can go. As before, you find the offsets for a called function and your desired function. You use readelf-s for that. That's exactly the same as before. Also the same as before, you calculate this offset difference. It's the difference between the address of your desired function and the function that was called in the program. Now here's where it gets a little different. You will load into a register. Now it doesn't have to be EAX. I've just selected EAX here because it's a very common register to use, and you will probably find some functions in your program that will call to an address based on EAX's value. So I will load into EAX my GOT entry for the called function, and then I will add to EAX my offset delta. So now I have the location of my desired function in EAX. And again, all I need to do is I need to find a location in my program or in a library where somebody is calling a function whose address is located inside of EAX or another register of my choosing. So this is how we can get around this problem that we don't know where things are. Earlier we talked about return to libc and how we could use that. We said there were a couple limitations. You could only call into functions that were used in the program. So this is slightly different. We are looking up these GOT entries and either modifying them or using them in order to calculate a GOT entry for the thing that we want to use. Now again, recall that the offsets into these libraries is constant and it's known. So you don't have to worry that, oh, well, this program, it's going to be different. Well, the base address will be different. The offset will be the same as long as they're linking in the exact same library. And here again is where we get into all of these dependencies. When we look at an exploit and it says this is the exact version of software, this is the exact version of the operating system that is required in order to do this exploit, this is why. So you can see also from this where writing your own custom exploit can be fun. So if you have a particular target and perhaps you've discovered a vulnerability using the things you've learned in this class, now you can try to exploit that vulnerability for your specific target. Might not be hardly possible if you wanted to generalize it and just say, hey, I want to get this exploit to work across many different versions of a program or operating system. But if you look at the specific case, you might be lucky. All right, so some other things that we have to talk about. In order to get this to work, you have to do something called ROP, Return-Oriented Programming. Sometimes people will call it ROPE, Return-Oriented Program Execution. Either way, this is what it is and how you do it. So the idea is pretty simple. You build up the function you want. So we've shown you how you can put new entries into a GOT, and we've also shown you how you can calculate desired offsets into a function. So here's what ROP does. You build up your function, and you do this by making use of chunks of code that come right before a return instruction. Now these code chunks are something we call gadgets. Now there are several tools that can be used to locate these gadgets. One of them, which I will use today, is called RP++. There's another tool called RopeMe, and another one called RobGadget. So there are several tools available. There's probably more than just 3 that I've listed, but these are 3 common ones that people might use. So how do I find gadgets? Well, first of all, I will say if you don't have a good understanding of assembly, this could be difficult. So this is another place where I will again recommend that if you aren't terribly familiar with assembly, you might want to have a look at our assembly courses here at Pen Tester Academy. So you can download a tool, something like RP++, and here's the link for that. It's on GitHub under Overclock. You can also search manually through disassembled code. Now, why would you want to do that? Perhaps you cannot find the gadget that you want using an automated tool. There isn't a nice clean call to add something to EAX and return, for example. So what you want to do is search manually through disassembled code. So why would you find things that weren't instantly found with the tool? The reason you won't find things with the tool that you can find manually is there might be a little bit of extra code in there that does something that may or may not be a problem for you. So, this extra code, let's say I want to do something with EBX. Perhaps this code also modifies EAX. And so I might be okay with that, depending on what I'm calling, or that might be a problem for me. If it's a problem for me, I might have to find some other code that I could use in order to negate the effects of that code. So this requires a pretty good understanding of assembly. This is a fairly advanced technique. And, how do I discover these chunks, these gadgets? Manually, I'm going to use a tool such as objdump. So objdump will show me what my program looks like when I disassemble it. All right, so let's go ahead and walk you through some of these things. So I want to start with my program, and I'm going to show you this is how in my simple program I can find those GOT entries. And there's not going to be a lot of them in my case. So I can do objdump -R on my program. In here you'll see there is a reference to start main, and then here is the only library function I'm calling in this very short program. Now again, if I had a longer program, I could be calling many functions. So this is the starting place. Okay, I have one whole GOT entry. Now, this is into libc. Now, we've been abusing libc for the last several videos, and that's not a bad thing. But I wanted to point out that in a larger program, there might be additional libraries on top of libc that would have useful functions that you could call. So that is my libc function. Now, what about my offsets into libc? So here I have my stir copy, GOT entry. I could say that entry is at 0804 A00C. So I'll just make a note of that. And by the way, we're not going to be able to walk you through a complete example because, number one, this program is really short, but I just want to show you the techniques that you would use for an attack like this. I think you'll see that it can be rather involved. And again, this does require a pretty good understanding of assembly. But for those of you that do have a solid understanding of assembly, I want to show you how you can use that in order to exploit some software. Okay, so the next thing we want to do is we want to look at our library. So once again, I'm going to run readelf-s, and if I run it, I will see my library functions. I can find the location of stir copy. Just pipe this to grep stir copy. And here it is, 007420. And look at my desired function. Maybe my desired function is system. So I can repeat this. Grep for system. And there's my offset, 0003 A940, or one of the exec functions. So we have a couple of different choices. Exec VE, exec L, etc. So I can pick the one that works best for me. And I might want to use something like exit as well. And I can find my exit function, which is right here. So once I have my function and my desired function, I can calculate this delta. So if I wanted to do this, I can calculate my offset. Now I could do this manually with my calculator as we've done before. I could also use Python in order to calculate this for me. That's sort of a personal choice as to which you want to do. One thing to be aware of, if you use Python to calculate this for you, recall that all these numbers are stored in little endian format. So you're going to have to take that number that you have in Python and convert it into little endian format if you're going to inject it into your program. So we're going to go ahead and we'll say that our offset into this, we've already used this before. We said that our offset into stir copy, let's remind ourselves of that. We said that stir copy was at 00074200. And we said that, let's say we want to go for system. System is at 0003A940. Okay, so those are our two offsets. So if I want to calculate that delta, let me go ahead and I will just start a new script. And of course, it will start with shebang. We'll just use Python 2 for this one. And I want to calculate some of these offsets. So I have my stir copy GOT. And that entry we said was at hex 0804A00C. We also have our stir copy offset is going to be at 00074200, and that is also in hex. Let me go ahead and use some tabs just to make this nice and pretty, and also I want to make sure I don't make any mistakes. Okay, and now we want to call system offset is 0x 0003A940. All right, now what? I want to calculate my offset delta. So my delta between stir copy and system is just going to be my stir copy address subtracted from my system address. So it's my desired function. My desired function is system offset minus stir copy offset. So that is that delta. So I'll just make a little note here. And my little note says for GOT overwrite, I'm going to set GOT entry at stir copy GOT to to what? To what is currently there plus my delta. So that's how I would use this for a GOT overwrite. What about a GOT dereference? For GOT dereference, instead, I'm going to do this. Load into a register. Doesn't matter which one. EX is a very common choice. The value at stir copy GOT, and then from there I will add my delta to the register, and then I jump to the register. Actually, not jump, I call the register value. I say call the function that's located at that register location. So that is how I could use this to call system. Now, what if I wanted to call other functions? The method is the same. No matter what I want to call, all I have to do is have a function that has been used, that has a GOT entry, and I can either overwrite that entry so that every time someone calls that function, it goes to the new function, or what I can do is I can use dereferencing. I can load the value into my register and then use that to go from there. So we're part of the way there, but we need to get all the way there. So what do we have to do next? Well, now we need to do that ROP, that return-oriented program execution, or ROP. Again, your preference, which one you prefer. So first thing I want to do is I want to go ahead and get a tool. And the tool I'm going to get is RP++. And it's a full C++ written tool that aims to find ROP sequences in a bunch of different binaries, tested on Debian, Windows 8, Mac OS X. And here it is. Now they say you could directly download things if you wanted, but we're not going to do that. We're going to build it ourselves. So here's the address on GitHub. Let me go ahead and load it. So let me copy this address, go back to my terminal. And I will go ahead and go to my root or home directory. And I'll do a git clone with this address. I will change to RP. And now I need to build it. All right, so how do I build this? Well, you'll notice that there is no makefile, at least not here. So you might say, well, how do I do this? Well, let's have a look at the README file. And it says you can use CMake, blah, 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 blah. And then it tells you a little bit about how to use it and how you can download binaries if you don't want to build it yourself. So if you do a CMake on // from the main directory, then it's going to go out and it's going to find everything that's needed and write it to disk. Right, so now if I do an ls, you'll notice that I have a make file. So I'll run make. This should be fairly quick because it's a somewhat small binary. And now it's given me a little bit of a problem because it does not have this engine, BEA engine. So what am I going to do? Apt search BEA engine. Didn't find it. So what can I do? I can go back here and see where might I find these missing parts. And I don't see this as a listed issue, and there's no wiki. So this is, sometimes the beauty of open source. Alternatively, if you just don't want to be bothered, you can always grab a binary. So let's do that real quickly just for the sake of time. And it says, where can I find these pre-built ones? They are here. And I would like a Linux 64-bit binary, please. And now I have it. And now I don't have to worry about it. So it's your choice, really. Which way do you want to go? Sometimes it's fun to build stuff. Sometimes it's better just to get on with it. And get her done, as a certain comedian would like to say. Okay, let me go back to my command line. I'm going to copy from my downloads RP lin64 to // I'm going to call it RP++. I'm going to do the standard thing, which is run a program because I don't understand how it works. I don't know how to use the different switches. Now notice if I just try to do /rp++ and I hit tab, it doesn't work because I didn't do this. Chmod plus x rp++. Now I can run rp++ -- help. And it tells me what it does and how do I use it. So let's go ahead and do this. So I want to find some gadgets. So how do I do this? I say rp++, and then I can give it my search path, the binary that I'm trying to look at. I can give it -r, find useful gadgets for future exploits. Arg is the gadget maximum size and instructions. So I can say no more than 4 instructions, etc. And there are some other things I can do. -at syntax if I like the AT&T syntax instead of the Intel syntax, which personally I do not. So I won't be using that flag. And there's some other flags as well. So let's go ahead and do this on our binary just to see how this works. So I'm going to run rp++. And I'm going to run it on -f buffer overflow -r, and I'll say 4 instructions, please. And so now it looked through there and it found a few gadgets. How many? 162. So here I am adding to AL. That's the low byte of the EAX register, this value. Here I'm calling EDX. So perhaps I want to load a value into the EDX register and then call that, right? So here's another little gadget and another little chunk of code that I found that I can use. So what do I do with this? What I can do with this is I can take these little bits of code and build the function that I want out of it. Now, of course, we've seen before if the function I want, I'm not going to get one function that does everything. That's just not realistic. So what I'm going to have to do is build it out of my gadgets. So I can take this and say, all right, let me go ahead and build up my gadgets. Now, I had a huge list here. I can say, let me start a little simpler. Let me go with R of 1. I just want one instruction before I return. And now I only have 63 of them. Here I see a call to EAX plus this certain value. Again, this is something I could easily use. So how could I use this? Okay, let's say I want to do a dereference. I can find something that will store a value in EAX. Then I can calculate the address I want to go to and subtract this value from it. store that in EAX, and then call this. So I could call this gadget here at this address, and I could use that in my sequence. So almost definitely, you're going to have to build a chain, just like we did with the return libc chains. We did that when we wanted to call more than one library function. You're almost guaranteed to have to call more than one gadget. So now we found some gadgets. Let's say we didn't find what we needed here. How do we find them ourselves? Again, we can find them ourselves using objdump. So if I do an objdump -d for disassemble on buffer overflow, I'm going to pipe that to less. Here's my program. Now this is using that AT&T syntax that I'm not a huge fan of, which is why it looks a little strange. I'll go ahead and hit Q, and you might say, well, I don't like that syntax. I want to use the Intel syntax. So how do I do that? And the answer is I can give it -M Intel. And now it displays in the more familiar, at least to me, Intel syntax. So again, we can look for functions and little fragments of functions called gadgets that will do various things. So here I have an add of ESP, I add 8, and I'm popping EBX, and I'm calling return. So maybe that could be something useful for me. So I can manually look through here and see if there's something that I could use that comes right before a return. Now remember the caveat if you go this route. You will probably find things that include additional code that you don't need, sometimes that you don't want. But depending on what it is, maybe you don't care. Okay, so let's try to put this together. And again, my intention here is not to walk you through an entire exploit. That is likely not possible with this simple little binary that we have anyway. Whereas if I had a larger application, this would be much more doable. So what can I do? I can convert all of this into an attack. And how do I do that? I will grab my information. So let me get out of here. Go back to my little Python fragment. So to build an attack. How does that work? If I want to build an attack, just like always, I have to get to my offset to where I'm going to inject my bad stuff. And I'm also going to have to add in a bunch of items. So I'm going to have to say, all right, what are my different calls? So I have to call, let's say, a couple of gadgets. So I will start with my last gadget call, and I will put these things on the stack. Why am I starting with my last gadget call? Remember, stack grows downward, not upward. So let's say that I had three gadgets that I called. So my last gadget call, I'm going to add it to the stack. So what do? I add to my buffer, or whatever you want to call it. Say buffer plus, say buff, because buffer is a reserved word, plus equals, and now I'm going to add my gadget address. So I can say, all right, I'm going to call this gadget. Maybe it's gadget 3. And then if I have any arguments to that gadget, so then I would add in gadget 3 arg1. Let's say it has 2 arguments for that call. Then I add the second to last gadget. So once again, I have to add in its address, gadget 2. And then any arguments that it requires. Let's say it just requires 1. And then, of course, I get down to this guy. I'm going to say, all right, I want to add in my last, or actually my first gadget. So it's going to have buff plus equals gadget 1, and then, of course, any arguments. So I'm essentially building out a fake stack and then what am I going to do? After I've added all of these things in, then I have to add in my original value that was going to overwrite this stuff. So this is kind of the general prescription for how this works. You're going to just add in these things. Now, again, just a warning, here I have these values. I'd said I'm going to do my math inside of Python. If I do that, I should reverse this order. I need to convert this stuff to little endent if I'm going to add it in. So how do I do that? Here's how I do that. I'm going to do that by defining a function. And this function is going to use struct to pack or unpack a value. Now, if you don't know what struct does, if you've ever actually had a Python class for me at the university, you will definitely know what struct does, because we use this all the time in forensics. But what struct does is it will convert essentially binary streams to and from C values, C variables. So I'm going to define a method, and I'll call it just little end, and it will take a value, call it num, and it's going to be very simple. All it's going to do is return struct pack, and it's going to convert my number into little endin format. And of course, I have to include struct for that to work. So now if I'm adding all of my values, I can say little end for all of these values. I probably should have named it something shorter, but I didn't. And this is going to convert all of these numbers into little endin byte streams. That's what the less than does. By the way, if you do some research on the struct function, if you go to python.org, you'll see that less than, and then you can either use I or L for a 4-byte unsigned integer. It has to be capital, by the way. If it's not capital, then it means a signed integer. All right, so that's kind of the general format for this. This is the general prescription for this. And once again, just like the chained return to libc calls, you can see this quickly becomes very complicated. So often you will have to find a bunch of gadgets, and you might also have to combine techniques. You might be able to use the overwrite technique for some bits of code, and you might have to use the dereferencing for other bits of code. Obviously, my preference would be to just do the overwriting. That's a lot simpler to do if you can manage it, but it's not realistic to assume that you can manage to do that all of the time. Okay, so this was a nice introduction to this technique of GOT overwrites and dereferencing. As a reminder, this is one but many videos and a whole family of courses that we have here at Pentester Academy, and everything you ever wanted to know about information security. And I look forward to seeing you in this course or another course soon. See you then.